So good afternoon or good morning to everyone, and welcome to what is currently the last scheduled extremal and probabilistic webinar. So before I introduce our speaker today, let me just mention this is being recorded, and we will post this recording on YouTube. If you have any question during the talk, either unmute yourself and just post the question, or you can also write it in the chat, and then I will read it out to our speaker. And in addition, we usually have some space for formal and informal questions at the end, including a part which is not recorded. And so now it is my pleasure to introduce Dan Kráľ from Masaryk University, and Dan will talk about quasi-randomness in various settings. So Dan, please.
Thank you, Honza, for the introduction. As you said, I will be talking about quasi-randomness, but I also want to talk about common graphs, and I just didn't smuggle them into the title. And but most of the talks will be about quasi-randomness, as you said, in different settings. And the talk is based on, or will contain results with various collaborators. I didn't put them on the first slide because I want to mention quite a large number of results, and I will just mention my collaborators when I will present the particular results. So let me start with a very broad introduction to quasi-randomness. And what we want to do, we want to understand when a certain particular combinatorial objects look as it would be generated by either uniform or some other procedure that we consider random enough. And in this talk, I will be talking about the approach using substructure density, which is a particular robust approach in the case of graphs. And I will mention also its extension to other combinatorial structures, permutations, and Latin squares in particular. So why we do care? So clearly, like in computer science, we might want to have a good understanding of how to measure that a certain sequence looks like pseudo-random or quasi-random, and this would be important for the randomization of algorithms, or actually also in the other way, that we might want to spawn some patterns in the encrypted text, and maybe use these patterns to break the cipher. And also, and this is related to this cryptography that I have mentioned, we also want to understand the independence in data, and actually some of the results that were proven only recently in combinatories existed in the disk use in statistics, and I will mention this when I will come to those results. So I don't want to stay on this abstract level too long, and maybe I will present the plan for the talk. So I first want to talk about quasi-random graphs, where I will not mention any new results, but I want to start with this area because it's a very classical area full of important and these days well-known results. And when I want to use this broad introduction as an excuse to talk about common graphs, where I have recently worked with various collaborators, including Honza Volec, who's co-organizing the seminar. And when I would like to briefly mention quasi-random permutation and quasi-random Latin squares, which is a more recent work with other group of collaborators. So let me start with quasi-random graphs, and I have mentioned like this is a very classical area of extremal and probabilistic combinatories that goes back to the 80s, to the work of Rödl, Thomason, and Chung, Graham, and Wilson. And essentially what we wish to understand when a graph looks like the R-range random graph. So the R-range random graph is perhaps the most standard model of random graphs, where we have n vertices and we put an edge between any two of them with probability p. And I should mention that it's maybe not the right approach to think of a particular graph if this graph looks like an R-any random graph, because every graph has a certain probability to be generated as the R-any random graph, and this probability is quite low. But one should think of a property of being quasi-random rather like a property of a sequence of graphs if the number of vertices going to infinity. And when we may ask whether this sequence has the properties that a sequence of R-any random graphs would have with probability 1. And this would serve us as the definition of quasi-randomness in the graph setting and also in the other settings that we will consider. So we will have a notion what is a random object, and based on that notion, we will wish to define what is a quasi-random sequence of objects of that kind. So let me start with recalling these classical results in the setting of graphs. And I said that the approach that I will present will be based on the subgraph density, and which is equivalent to the homomorphic density that I will now introduce. So if I have two graphs A and G, then the homomorphic density of H in G is the probability that if I take randomly an injective mapping from the vertices of H to the vertices of G, then this mapping will be a homomorphism of H to G. So in particular, if H is an edge, this is just the density of edges, because the probability that I map the two vertices to an edge is essentially the density of edges in the graph. And I will say that a sequence of graphs, maybe a sequence that looks like this, is quasi-random if and only if the homomorphic density of every graph in the sequence converges to its expected density in the sequence of the R-any random graphs. So if I take a sequence of R-any random graphs with the number of vertices increasing, then that sequence would satisfy this definition with probability 1, and this definition will serve to me as the definition of a quasi-random sequence of graphs. And this particular notion turns out to be very robust in the sense that it's equivalent to many other properties that the sequence of R-any random graphs have with probability 1, and any of these properties actually implies that the homomorphic density of any graph converges to its expected value. Perhaps if one haven't seen quasi-random graphs earlier, like the first property, which actually is somewhat surprising, is that one doesn't have to look at all graphs, but it's enough to look at the density of edges and the homomorphic density of C4s. So if I have a sequence of graphs where the homomorphic density of edges, the density of edges, and the homomorphic density of cycles of length 4 converges to P and P to the 4th respectively, then in that sequence, the homomorphic density of any graph would converge to its expected density in the sequence of R-any random graphs. So clearly the implication from the first line to the second is trivial, and one may find it somewhat surprising that even if the first line talks about infinitely many graphs, it's actually a property of two graphs only. And when there are some other properties, which I also find like maybe not so surprising as this second line, but I found them saying that this is a very robust definition of quasi-randomness. Where, for example, one may look at linear size subsets of vertices. So this n is now not the total number of vertices in the graph, but it's the number of vertices in a subset of vertices of the host graph or of the graph in a sequence. And I want the number of edges to be roughly what one would expect to be in the R-any random graph, which means Pn squared over 2. Or instead of looking at the number of edges inside subsets, one may be looking at the number of edges between subsets. And again, if I take two linear size subsets A and B, then I expect the number of edges between them to be P. And if roughly this holds for all linear size subsets, then again, it implies the previous three properties. And this is also equivalent to a more spectral approach, that one can look at the spectrum of the adjacency matrix in the sequence of R-any random graphs. The spectrum will have one eigenvalue concentrated around P times n, and when all the other eigenvalues will be sublinear and n if n is the order of the graph. And again, like if I have a sequence of graphs, but my spectra do satisfy this property, meaning one eigenvalue after normalization by n converges to p and the others to 0, when that sequence is quasi-random in the definition we have seen here. So this is a very robust definition of quasi-randomness, and I want now to briefly introduce the terminology from graph limit and cast the notions that I have just introduced in the terms of graph limit, and then use this terminology to present some results that we have recently proved on common graphs. So I will not go into details. I will not even be saying things really rigorously, but I still want to define the concepts and say few things about them. So let me introduce the notion of convergent sequences of graphs and their analytic representations, which are called graphons. So a sequence of graphs is convergent if the homomorphic density of every graph in the sequence converges. So in particular, if I have a sequence of quasi-random graphs, then I'm saying not only that the homomorphic densities of every graph converges, but I'm saying to what it converges. So this is a more general definition that I just require the homomorphic densities to converge, but I'm not prescribing what the limit should be. So in the sequence of quasi-random graphs, I do prescribe that the limit is the expected homomorphic density of H in the R-any random graph, but in the definition of a convergent sequence of graphs, I just do require that the homomorphic density converge. And when I have a sequence of graphs, a convergent sequence of graphs, I can try to represent it by an analytic object, which is called a graphon, which is formally a symmetric measurable function from the unit square to the unit interval. And one can think of this function as a continuous version of adjacency matrices. So for example, if I have a sequence of complete bipartite graphs where the two parts of the graph converge to the ratio 1 to 2, so I have roughly 1/3 of vertices on one side, 2/3 of vertices on the other side, when where adjacency matrices would look like this. So I will have two squares of zeros corresponding to the independent sets, to the two parts of the complete bipartite graph, and ones between them. And the graphon that represents this particular sequence of graphs will be graphon that looks like this. So in order to have the analogy with the adjacency matrices, I put the origin of the coordinate system to the left top corner. I have two areas which are white, which corresponds to zeros, and this graphon would have ones on these two areas. And I put here some other graphons. So the graphon that is constantly equal to P, which I depicted by this gray, would correspond to the quasi-random sequence of graphs. This graphon would correspond to the sequence of graphs that looks like a sequence of complete bipartite graphs with parts of equal sizes. And this graphon would correspond to a sequence of graphs where I do see a complete graph on roughly half of the vertices, quarter of the vertices, 1/8 of the vertices, and so on. And at this point, I should mention that even if this analogy seems quite easy and maybe natural, like in order to establish a connection to the convergent sequences of graphs, in particular, if one defines a notion of so-called double random graphs and use it to define the homomorphic densities of graphs in the graphon, then to make a connection between graphons and the convergent sequences of graphs, one needs to use some tools from combinatorics, and not only combinatorics like regularity decomposition, martingale conversions, and so on. So even if this looks like something very natural and most likely easy, actually it's not so easy as it may look at the first glance when I start thinking of making the connections really proper. And when using this language, the sequence of graphs is quasi-random if and only if the homomorphic density of every graph in the limit is what one would expect in the R-any random graph, which is actually equivalent to the graphon to be equal to 1/2. Let's say we're talking about the R-any random graph G and 1/2 to be equal to 1/2 almost everywhere. And this can be now the result that I have mentioned, that instead of looking at the homomorphic density of all graphs, it is enough to look at the homomorphic density of K2 and C4, can be generalized by saying that if I have a graphon where the homomorphic density of K2 is P and the homomorphic density of C4 is P to the 4, then that graphon is equal to P almost everywhere. And this actually implies something which might not be obvious, but this actually implies it at the first sight. So this implies that the homomorphic density of C4 in any graphon is at least the 4th power of the homomorphic density of K2 in that graphon. And the reason why this, the characterization of quasi-randomness using K2 and C4 implies this inequality is that if I had one graphon where the homomorphic density would be larger and one graphon where it would be smaller, I could continuously combine these two graphons together and obtain a graphon that is not quasi-random and where the homomorphic density of C4 is equal to the 4th power of the homomorphic density of K2. And this inequality, so now we know that there would be an inequality and we know which way, because for example, in the complete bipartite graph, the inequality is strict in the way that there are more C4s than the 4th power of K2s. And this inequality is a subject to a famous conjecture of Sidorenko, that actually there's nothing special about C4s, but it should actually hold for all bipartite graphs H. So if I want to formulate Sidorenko's conjecture, which is one of the most significant open problems in extremal graph theory in the terms of graph limits, when I would be saying that the homomorphic density of any bipartite graph is at least the edge density in a graphon is at least the edge density in that graphon powered to the number of edges of that graph. And sorry, I have a mistake here. And the conjecture, the Sidorenko's conjecture can be generalized that if I have a bipartite graph that contains at least one cycle, so this acyclic should actually be containing at least one cycle. So I'm not sure whether I can quickly write here, but let me try. Contains, I don't have a tablet here. Contains cycle. So if H is bipartite and contains a cycle, then the equality in this inequality would hold if and only if the graphon would actually be the constant graphon with the appropriate density. And there have been a lot of partial results, in particular due to Sidorenko himself, who proved the conjecture for the inequality for all trees, the conjecture, and also like even cycles, and there have been various extensions by various authors. I would particularly like to highlight Szegedi's work using the entropy method. And I would also like to mention that we also have local versions of the conjecture, meaning that if I have a graphon that is not far from the constant graphon that the conjecture holds, and there has been a one version due to Lovász and a stronger local version due to Jacob Fox and Van Wey, which was announced about 4 years ago, but the paper is not yet available. And so now I might like to slightly detour from quasi-randomness and go to common graphs, but maybe I will pause here for a second and take any questions if there are any. I do see that there are no questions in the chat, but please feel free to unmute and just ask a question if you have any. So let me continue. So I want now to detour from the main topic of the talk, which is quasi-randomness, and talk about a very closely related topic of so-called common graphs. So we all know Ramsey's theorem, which says that if I have a 2H coloring of a sufficiently large complete graph, then it always contains a monochromatic copy of any graph. So for every graph H, where exists N, such that if I have a 2H coloring of the complete graph with at least N vertices, so in particular with N vertices, when it contains a monochromatic copy of H in one or the other color. And of course, it's natural to ask, like, how many monochromatic copies such a 2H coloring must contain. And it's not hard to see, just using Goodman's bound, that the number of monochromatic copies of a triangle is minimized by the random 2H coloring. So in fact, it's minimized by any 2H coloring where every vertex is incident with roughly the same number of edges of one and the other color. And this led R dash to conjecture that there's nothing special about K3, but in fact, if I take any complete graph, then the random 2H coloring will be minimizing the number of monochromatic copies of that complete graph. And this conjecture was further extended by Burr and Rosta, and who conjectured actually this property all graphs do have. So let me now say that instead of saying this property, I wish to be calling the graph having this property common. So formally, a graph H is common if the random 2H coloring minimizes the number of its monochromatic copies, which I can formulate in the language of graphons as that the homomorphic density of H in W plus the homomorphic density of H in 1 minus W is at least what one would expect if W would be the graphon equal to 1/2 everywhere. So one can think of W as representing red edges, 1 minus W as representing blue edges, and when the sum of these two quantities just represents the proportion of monochromatic copies. And as I have mentioned, the conjecture of R dash, who conjectured that the random 2H coloring minimizes the number of monochromatic copies of every complete graph, says that every complete graph is common, and Burr and Rosta extended this conjecture to all graphs and asserted that every graph should be common. And this conjecture is definitely not true. Sidorenko proved that a triangle with a pendant H is not common. Thomason actually proved that no complete graph is common. So this proving the conjecture of R dash, of course, with the exception of triangle, where we know that it holds. And then generalized this result and showed that no graph containing K4 is common, which of course implies that no complete graph is common. However, at this point, we know there are various common graphs that I will mention on the next slide, but we don't have any even conjectured characterization about on common graphs. So let me mention some positive results. So Sidorenko's conjecture implies that the density of every bipartite graph is minimized by the random graph with that the constant graphon or the random graph with an H density. So this would imply that all bipartite graphs are common. And while we know many bipartite graphs to satisfy Sidorenko's conjecture, we don't know even that bipartite graphs are common, and more or less we only know the bipartite graph satisfying Sidorenko's conjecture to be common, or those for that we can prove Sidorenko's conjecture. However, there are also non-bipartite graphs known to be common. So in particular, Sidorenko proved that and every odd cycle is common. So that this is an extension of the result on triangles. So we can replace triangle with C5, C7, and so on. And we still will have that these graphs are common. Jagger, Stovicek, and Thomason, they showed that every even wheel is common. So if I take a cycle of an even length and add a vertex that is adjacent to all the vertices of the cycle, and this graph would be common. And then with Hamed Hatami, Honza Hladky, Sergei Norin, and Sasa Rasborov, we found the first example of a 4-chromatic graph that is common by showing that the 5-wheel is common. So the 5-wheel is a graph obtained from the 5 cycle by adding a vertex adjacent to all the vertices of the cycle. So in particular, there has been no graph with chromatic number at least 5 known to be common, and this was one of the points of the work that we started with Jan and Fan. So one of the results that I want to mention at this talk, and we're working intensively on preparing the draft to be posted on arXiv soon, is that we're able to construct a connected Electromatic common graph for every L. So as I mentioned on the previous slide, the maximum chromatic number of a common graph, it was known before, was 4, it was the 5-wheel. And the construction, so I sketch here the construction, I don't want to talk too much about the proof, is that we take a graph with a high chromatic number with somewhat large graph. I believe that if we try hard, we can decrease this parity somewhat lower. I'm not claiming we can decrease it to 4, but maybe we can decrease it to 10 at the expense of quite some technical work. So we take a high chromatic graph with large graph. We take a large complete bipartite graph, which we will know that there will be a lot of copies, or basically once we deviate from a random coloring like this graph, the number of monochromatic copies of K2n to n will be increasing, the sum and the two colors. And when we join this large complete bipartite graph by long path to this high chromatic graph with graph and this parity. And the idea is that if we don't deviate too much from the coloring, we still have a lot of copies of A0. We have many more copies, or somewhat more copies, of the complete bipartite graphs, and we can use this long path to go from the source of monochromatic copies of the bipartite graph to the source of monochromatic copies of A0 and join them together. However, this idea, while it sounds simple, there's actually a lot of technical work to be done, as you may imagine, because even if I'm saying we will have copies, they might be in different colors, the paths might somehow be not be connecting them properly. So some work needs to be done, and it can be done, but it becomes somewhat technically challenging, and I don't wish to go into the proof. But I want to mention another result that we proven with Honza and Feynman, in addition with Sergey and John, and that's a consensus generalization of the notion of common graphs to the notion of K common. So I say that a graph is K common if the random KH coloring minimizes the number of monochromatic copies among all KH colorings. And prior to our work, there was no non-bipartite K common graph known for K at least 3. And what we have shown, we shown that there exist connected free chromatic K common graphs. And I should emphasize here that this connectivity here is important, because it's not so hard to show that if one wishes to abandon the connectivity when taking an odd cycle, and the large complete bipartite graph will do the job. And these are the graphs that we constructed with the assumption of connectivity. So again, we have a large complete bipartite graph, and on some of the vertices we have these 5 cycles sitting, and when we need to apply some algebraic arguments showing that the gain by taking this complete bipartite graph in terms of how many monochromatic copies we get balances what we may possibly lose by needing these vertices on this side to be contained in odd cycles. And this paper is already on arXiv and is accessible. And before leaving the topic of common graphs, I want to mention yet one more recent work, and namely I want to mention some work on so-called locally common graphs. So the common graph, so maybe I go back to the definition, requires that for every graphon, if I look at the homomorphic density of H in that graphon and the complement of that graphon, then it will be at least what one would expect to be in the one constant 1/2 graphon. And the notion of locally common requires that one is just looking at the small deviations from the random coloring. So what one requires is that if the random coloring would correspond to the half graphon, and now we do a small deviation which corresponds to adding or subtracting something, which I will be representing by U, and I want that for all these small deviations from the random coloring, the number of monochromatic copies always increases. So clearly this is a weaker notion when being common, because there's no restriction what happens in colorings that are substantially different from the random one. But at least like we know that instead of being a global minimizer, the random 2H coloring is a local minimizer. So the local version of, and similarly, one can also formulate the local version of Sidorenko's conjecture, where we have a good understanding, and we know when the graph is locally Sidorenko. So if I'm just minimizing the number of copies, not number of monochromatic copies, when this is a property of even graph, and this was proven in one version by Lovász and in the Strogan version by Fox and Way. And now actually I will mention what these weaker and stronger versions are, because we may define this locality in two different ways. So the stronger version of the locality is that one wishes to have a universal epsilon, such that if one performs the deviation according any deviation that is at most epsilon 0, then the graph will stay locally common. The other notion is that we first fix the deviation, and for that particular deviation, we want to fix epsilon 0 such that if we go in this direction and we don't go farther than this epsilon 0, then we have the commonicity, or we have the Sidorenko property. And in the case of Sidorenko property, these two notions coincide in the sense that a graph is locally Sidorenko in one or the other notion, if and only if it is even graph. However, in the case of being locally common, the two notions differ. And Choka, Hubai, and Lovász, they showed that if a graph contains K4, when it's locally common in this first notion, and is not locally common in this first notion, but is locally common in the second notion. And what we did with Robert Hancock, Matthias Kearns, and Honza Volet, we actually look at the expansion of this expression for the homomorphic densities. We look at the first 12 Taylor series, first 12 times of its Taylor series, and based on that we able to do the classification. So we're able to say that for some of the graphs H, so for example, if H contains C4 or it contains C6, but it must be locally common in this sense. For some cases, like for example, it contains no C4, no C6, no two copies of C3 sharing a vertex, but it contains a copy of C3 and C5 sharing a vertex, but it's not locally common. And in some cases, we just know that all the first 12 terms are 0, so one would need to continue the analysis. However, at this point, I could have prepared, maybe I should have prepared a slide like the characterization when we go to this level of 12 is actually, we have kind of a diagram showing where one travels, which has something like about a dozen different conditions. So the characterization looks quite complex, and we definitely do not have a conjecture what would be the characterization of locally common graphs in this sense. So I think I should stop here again, because I completed the second part of my talk. I should mention that the third and fourth part will be shorter, but when the first two. And again, I think it might be a good time to take questions if there are any. It does not seem to be the case. So in that case, let me talk briefly about quasi-randomness in some other settings, and I will be talking about quasi-random permutations and quasi-random Latin squares. So I wish to I do apologize. I will be missing a slide. Sorry. So when I was preparing the talk, I just noticed that I accidentally deleted a slide. So I do apologize for that, but let me still try to go. So I want to say that a sequence of permutation is quasi-random if the density of every permutation in the sequence converges to what it would be in a random permutation. And if I take a random permutation in the, let's say in the uniform setting, so what I will be doing is that among all permutations of order n, I take every permutation with probability n factorial. When I expect to see any small pattern with the probability 1 over k factorial. And I should now explain what I mean by a subpermutation. And because I was not careful when preparing the talk, I was like trying to reuse some old slides, and I missed the one where I would explain what I mean by a pattern. So let me draw an example. So the example will be here. So I'm taking a permutation 1, 2, 3, 4. 1, 2, 3, 5, 4. So this is a permutation or a visualization of the permutation 1, 2, 3, 5, 4. And a subpermutation will be that I choose some of these points. So maybe I choose this point, and this point. And I read them from left to right. And I look what these points are. So this point is the smallest. So this subpermutation of this permutation 1, 2, 3, 5, 4 would correspond to 1, 3, and 2. And when if I want to say what is a density of a certain 3-point permutation, I take all the triples, or in other words, I choose a triple randomly, and I look what subpermutation or what pattern that particular triple induces. So this would give me a definition or of a notion of a density of a small permutation and a large permutation. And I will say that a sequence of permutation is quasi-random if and only if the density of every k-point permutation converges to 1 over k factorial. And Graham asked if, similar to graphs, where exists some k0, such that a sequence, if permutation is quasi-random in the sense that the density of every k-point permutation converges to 1 over k factorial, if and only if the density of every k0 permutation converges to 1 over k factorial. So again, instead of looking at all permutations, one would be just looking at permutations or permutation patterns, if one wishes, of certain size or order. And it's not hard to observe that the answer to this question is negative if k0 is free. And I have prepared here a picture or two pictures. So if I look at the permutation which has an interlace increasing and decreasing sequence, so basically this corresponds to having 1, 3, 5, and so on. This corresponds to n minus 2 and so on. Let's say n is odd, n is even. So if I interlace an increasing permutation and a decreasing permutation, when the density of 1, 2, 3 in this permutation is quarter. If I take a permutation that looks like this or can be visualized like this, the density of 1, 2, 3 there is 1/8. And if I continuously modify this permutation by first thinking of these two as very thin rectangles, and I start opening them, and eventually they meet and form a square. Then somewhere in the middle, I get a permutation with 1, 2, 3 will have density 1, 6. Therefore, 3, 2, 1 will have a density 1, 6. And the complementary 4 patterns will sum to 2 thirds. But because the picture is symmetric, both according to the vertical and horizontal axis, one will derive that the density of any 3-point pattern is 1, 6. And so this is an example, or this would be an example of a large permutation where the density of every pattern is roughly 1, 6. However, with Oleg Pigurko, we actually proved this question of Graham, and we showed that the answer is positive for k0 equal 4. And we have a proof using actually permutation limits. And when it turned out that the answer to Graham's question was known in statistics for more than half a century, in particular Hevding results from 1948, essentially is equivalent to answering the Graham's question in positive for k0 equal 5. And when Yanagimoto's result from the early 70s is equivalent to the result that we have proven with Oleg. So this is the connection to statistics that I had promised to mention. And as you may see, based on the age of the results, it's not that I was just trying to make some ad hoc connections, but really these results do appear and actually are used in statistics for testing independence. And of course, like now from the combinatorics point of view, the interesting question is whether we actually do need to test the density of all permutations to know whether a sequence of permutations is quasi-random. So Graham's question was saying we look at all permutations of certain order. And of course, instead of looking at all 24 4-point permutations, one can be looking at a subset. And this has been some joint work or some work that I have been doing with various students, postdoc, and collaborators of mine. So in particular with Tim Chung, John Noel, Yanni Pehova, Mariam Sharizadeh, and Nonzavolet, we look at sets T, such that instead of looking at the density of every individual permutation in that set, we just look at the sum of the densities of permutations in that set. And we managed to classify all such sets T that do have the property that a sequence is quasi-random if and only if the sum of the densities of the patterns in the set T converges to the number of patterns divided by 24. So in particular, if I know that every pattern, every permutation in this set T has density 1/24, then it implies the quasi-randomness. But this notion is weaker in the sense that I do not insist that the individual densities are 1/24 when I'm just looking at the sum. And this is the characterization. So the set T, which is a subset of S4, has this weaker property if and only if it is one of these 4 sets of their complements. So I have put here some sets which actually minimizes the sum, and where complements do maximize the sum. And these are the sets. That's the result. However, we do not know what is the minimal subset of 4-point permutations. So we know that a minimum subset would have at least 8 permutation contained. But a recent result of Martin Kurečka, who was my bachelor student, actually he managed to show it using actually quite a nice argument that even if I remove the assumption that I'm looking at 4-point permutations, I'm just looking at permutations of all orders, then I need to take at least 4 permutations. So there is no set of 3 permutations, whatever orders one takes, that would force the quasi-randomness. So for every triple of permutation patterns, one can find a sequence of permutation that these 3 patterns will converge to 1 / their order factorial, but the sequence won't be quasi-random. And now I wish to leave the world of permutations, again, maybe pause for half a minute to take questions, and we'll very briefly mention some recent results that we have on Latin squares. So Joel has a question. So you muted, Joel.
Can you hear me now?
Yes.
Yeah, okay. So for graphons, there are the generalization of quasi-random graphs. There are other graphons that are finitely forced. In particular, things coming from finite multipartite graphs, but other things too. Is there a similar thing for permutations? You talk about being forced to be quasi-random, but how about being forced to be something else?
Yes, so we actually do have a generalization of, so where is this result that you actually did also some improvements in terms of how big graphs want to take about step graphons. So, and we do have a generalization of these results to permutations. Like, of course, there are various ways how to generalize, but from our point of view, the most natural is when thinking of a clique as an increasing permutation and thinking of an independent set as a decreasing permutation, because this would correspond to permutation graphs. And we can show that if one has any permutation which has like finite structure in the sense that one has a finitely many increasing and decreasing segments, but it is finitely forcible. And this is a joint work with Andrzej, Terka, and Roman, if I'm not mistaken. So Terka Klimoshova and Roman Glebov were both, well, Terka was a student, Roman was a postdoc of mine, and this was, we did it I think before Andrzej joined me as a postdoc even. And I know he's listening, so he can in terms of timing.
Okay.
Jan is saying that Andrzej agrees that it was like this.
Okay.
So,
Thank you very much.
yeah, thanks. So I very briefly mentioned Latin squares, and I will just state the result. I will again not talk too much about the proof. It's using analytic argument. So in a Latin square, for me, it will be just a matrix that contains numbers from 1 to n. So I have here a particular example of a Latin square of order 5. And similarly to permutations, I will define a pattern density, but I choose some rows and columns. So in this example, I've chosen the second and fourth row and second and third column. And then I will just look at the relative order, similarly to permutation of the numbers that I do see. So 1 is the smallest, 3 is the second smallest, 4 is the third, and 5 is the largest. So if I have a large Latin squares, and I choose very few rows and very few columns, the numbers that I do see in these rows and columns will be mutually different. So the patterns that I will be particularly interested will be patterns that all the numbers are different, because those that some of the numbers repeat, they appear with in the limit with probability 0. And the limit theory for Latin square was built by Frederick Garbe, Robert Hancock, Honza Hladký, and Mariam Sharifzadeh. And I should mention here that there are many things that one needs to overcome. So first of all, one needs to think of the right notion of regularity, but also like a very strong property of graphs and the permutation in terms of limits, which is rather easy in those settings, is so-called sampling. So if one gets a large graphon, and obtaining a graph which has a similar structure as the graphon is not hard, but it's actually not easy and requires the recent powerful results of the existence of designs in the case of Latin squares. And they conjectured that similarly to our quasi-randomness, so quasi-random would mean that the density of every pattern converges to what one would expect, so namely the number of its entries factorial. And they conjectured that there would exist some K and L, such that instead of looking at all the patterns, it would be enough to look at patterns which are K times L. And with Jay Cooper, who's my PhD student under Lamaison, and Samuel Moore, two postdocs of mine, we actually showed that the answer to this conjecture is positive. Namely, we showed that if the density of 2 times 3 patterns converges to 1/720, then the sequence is quasi-random, the sequence of Latin squares. And we showed that this 2 times 3 cannot be replaced with anything smaller. So there would be 2 natural things that one would think, 2 times 2 or 1 times L for any L. And in either case, excuse me, we're able to find a sequence of Latin squares where the pattern density of all patterns 1 times L converges to L factorial, or all the density of all 2 times 2 patterns converges to 1/4 factorial, and it's not quasi-random. And again, the tools that we're using, we're actually using the limit theory built for Latin squares, and we just apply analytic arguments to prove this. And I was told that I should talk for about 50 minutes and then take questions. I think my 50 minutes just ran out. So let me just mention some open problems and finish. So clearly, like one of the open problems is the classification of common and locally common graphs. In either case, we don't have even a conjectured classification. I think we quite far, in particular in the case of common graphs. Maybe one can imagine doing something for some notions of, we have seen these 2 notions, the stronger one and the weaker one of being locally common. So maybe where one can do something, maybe also in the belief that Sidorenko's conjecture also tend to be easy in the local case. But the classification of the original notion of common graphs seems to be completely out of our reach. And I personally find quite interesting and maybe more approachable questions concerning permutations. So in particular, finding the minimal, or at least minimum, quasi-random forcing subset of 4-point permutations. So we know it must have at least 4 elements and at most 8 elements. And in general, finding minimal or at least minimum quasi-random forcing sets of permutations. Again, due to the result of Martin Kurečka, we know that such a set must have at least 4 elements. And we have seen in many different settings. I have mentioned here graphs, permutations, and Latin squares, but similar results do exist, for example, for tournaments or directed graphs. But if we define a quasi-randomness of relational structures, then quite often it is captured by checking the densities of finitely many substructures. And the question that comes perhaps to our minds would be whether there is some common generalization of what kind of combinatorial structures do possess this property. And it would be nice to have some, maybe not unified theory, but somehow like having some condition when we can expect this kind of finiteness or finite characterizations of quasi-randomness. And with this, I thank you for your attention.
So thank you, Dan, a lot, and please unmute yourself if you want to thank Dan. So are there any more questions?
If I could ask a second question. First, a comment. I'm very pleased that you referenced Ron Graham, who was an absolutely vital person in my life and for many other people. And it's nice to see that his work is being continued by you and many others. So that's really a personal pleasure for me. But my question on common graphs, perhaps the most beautiful conjecture of Erdős that turned out to be completely false, but is it possible that there's some graphs which are not common graphs, but for which the optimal W has some particularly simple form? And are these possible to study in some way?
That's a very interesting question. So the answer is I don't know. I mean, I would believe that there must be such graphs.
Yeah.
But I don't know. And I mean, we still don't know like the exact minimizer for K4, which we know that there is this beautiful construction of Thomason that would not yield something nice, at least from the limit point of view. Mm-hmm. But maybe it's not the right minimizer. I don't know. The answer is simply I don't know. I would be surprised if there is no complex graph that would have a somewhat nice minimizer that would not be quasi-random, but simply I don't know.
Okay, thank you.
So Dan, let me ask the following question in an informal way, but it could be made more formal. What is the simplest kind of property that can distinguish a quasi-random graph from GNP?
The simplest property.
How large complete graph it has. So the quasi-random graphs, if you have a quasi-random graph and add little n square edges, it still stays exactly the same quasi-random graph. And this can change the size of the largest complete graph. So that's the simplest property which distinguishes. There are these papers on that hidden complete graphs in a random graph and so on. So this question was there for long ago.
Yeah, that's a good example. I wonder if saying that a graph is quasi-random says that, of course, quantifier-free formulas have the same probability in the quasi-random graph that they do in GNP. Suppose we add one quantifier. Can we get something which then fails? I don't think the example of size of largest clique would fit into this framework.
Yes, but still I would argue against your opinion in the sense that Hamiltonicity cannot be described by simple formulas, we know, and they are very important in random graphs. So this quantum, you may say that it's important, but what I'm saying that quasi-randomness is so good, and this was which in the Wilson Graham Chung paper was very good, that it is invariant, it's a robust notion. And the randomness is not a robust notion because you can change it locally. As I said, the simplest case is the size of the largest complete graph, but many other things, whether it has isolated vertices. So obviously a quasi-random graph can have isolated vertices. Random graphs do not have isolated vertices. So
yeah, that's a good example. I agree that the notion is a good one.
yeah, it was a good, yeah.
I'm just curious, you used different settings in this talk, internal settings. Is it possible to make some connection between extremal graph theory to weighted graph? For example, is it possible to use random graph model to make weighted graph and study that models in some ways which is sensible in graph theory? It's a general question. I think between, for example, in group theory, we can some models in graph theory where they are commutative. We can define the edge or something like that. So is it a study to do in this form using random graph to make a new graph, but in a weighted graph setting?
So I'm not sure I completely got the question, but in some sense, and that's not what I have mentioned, because I didn't want to talk too much about graph limits, but somehow one can think of graphons as some kind of generalized notion of R-range random graph model. But and it was known also under the stochastic block model in the case of step graphons, which I have also mentioned in relation to this forcing result or proven by Lovas and Schorsch, and then like with better bounds given by Joel. And so one can think of graphons as kind of a model for more general notions of graph randomness. I'm not completely sure whether this answers the question well, but I had a feeling that it might go in the spirit what you're asking.
Thanks.
So I have one question. Would you, permutation densities, they don't quite correspond to subgraph densities. They correspond more to induced subgraph densities.
Mm-hmm.
So could you find an alternative definition more in the spirit of ordinary subgraph density so that you could then formulate some sort of Sidorenko conjecture for permutations? And of course, the density there would be the proportion of increasing permutations.
Mm-hmm. That's an interesting question. I don't have a good answer to it. Like, I mean, basically, like you're asking what is the analog of bipartite graphs for permutations, whatever it could mean. And I do agree that also the density as we're working with it is more induced than homomorphic. But I don't have an answer.
Okay, thanks.
You had a paper, a lecture on these things when you, at least Klimosova had a lecture when we were in Metagraph. So what was it about? This was related to this area.
So I think that's the paper I mentioned to Joel's question. if I'm so where I have several papers with Terka because she was my student. But in regard to the permutations, I have this one on forcing these structures which correspond to the step graph ones in the permutation graphs. But and when but I'm not sure whether this is the paper that you're referring to.
I think, but I'm not sure that you proved that if all the 4 lengths permutations are of the right density, then everything is of the right density. Maybe.
Yeah, but that's the result with Oleg.
Yeah. This is what I would just.
Overqualified, but you have been also present. I don't remember present in the class. So it's this result with Oleg.
Yeah. This is what I was asking because. Okay.
But actually, maybe, and I don't know, like so maybe let me comment a little bit more on the question of Jan, and I don't know whether the answer will be satisfactory, but and I don't know how to define like homomorphic density of a permutation. However, in the case of graphs, if I want to define a homomorphic density of a graph, I would take it as some sum of induced densities of graphs. And here we have some minimizers for quasi-random permutations. And maybe one of these sums can be viewed as a C4. I don't know like the right view, but we know that a quasi-random graph one minimizes the density of C4. And I'm offering you here a sum of permutations, for example, this one, that is minimized by the quasi-random permutation. And you can see it has some structures because basically you split into quadrants. And when you either decide you will go for the top left or the bottom left, or the bottom left and the top, sorry, bottom left and top right, or vice versa. And then within you have like always increasing or decreasing. So it has some structure, but I don't know how to cook up a good definition of a homomorphic density from it.
Yeah, thanks. I mean, I never claimed it was an intelligent question. But...
No, but for example, one thing that actually I think might be interesting to see, and this might be again related to all like the step Sidorenko and weekly norming. So we know that C4 is actually one that actually corresponds to your work on like defining graphons. But like whenever you kind of take an averaging, like the density of C4 decreases, and it would, for example, be interesting if, for example, this sum has a similar property for permutons. And the answer is I don't know.
Okay. Yeah. Thanks.